Good afternoon, everyone. Thank you all for joining the Australian Water School today for another informative webinar from the TUFLOW team. Today's topic is computer hardware for hydraulic modelling. My name's Tegan Burke, and I'm an Associate Principal Engineer and Flooding Technical Lead with BMT based in Brisbane, Australia, and I'll be your chair for today's webinar. We have a widespread audience of people from around the world interested in today's modelling hardware topic. So it's great to see you all, and I'm sure you'll leave with many valuable insights today. Our presenters today, who I've had the pleasure of working with during my time in the TUFLOW team, are Jaap van der Velde and Greg Collicutt. They will be taking you through purchasing advice and insights on best fit hardware for hydraulic modelling. We'll also have Mitchell Smith moderating the Q&A in the background. So Greg is TUFLOW's senior GPU code developer and has over 25 years experience in writing scientific modelling software. And Jaap is an accomplished associate principal software architect with nearly 8 years of experience at BMT. So Greg, Jaap, would you like to say a few more words about your background?
Oh, thank you for that, Tegan. Yes, look, welcome everyone. Thanks for joining us today. I'm Greg Collicutt. I work with Team TUFLOW here, writing the GPU software that powers HPC, as well as TUFLOW FE, version for ocean and estuaries. I've been in TUFLOW for about 10 years now, and it's been an absolute ride. I'm doing what I love, and that's what gets me out of bed every day to come to work. It's so much fun.
Yeah, thanks, Greg. Thanks, Tegan. My name is Jaap van der Velde. I'm from the Netherlands originally, as you may be able to tell from my name. I've been in Australia for about 8 years now. Been working with BMT for all that time, working out of their Brisbane office and living there as well. Well, not in the office, but in Brisbane, obviously. I work for BMT, or used to work for BMT as a senior ICT consultant. I'm now part of the TUFLOW team, where I do development work mostly on running TUFLOW in the cloud and on infrastructure all over the place, which I think is relevant to this particular talk. My background is in computer science, and I specialize in software engineering.
Great, thank you very much both. We'll have a look at the poll results now, see what information we've got from our attendees. Okay, so Greg, would you like to talk to the results of the poll there?
Okay, thank you, Tegan. Okay, well, we've obviously got a spread of ages there from people less than 5 years, but actually quite a significant number of people who are attending are actually got over 10 years experience. So that's good. We have a few people in the IT admin and developer roles, which we were hoping to actually target this webinar towards those people as well, to be able to help them with some of the hard choices that have to get made. Okay, my poll window has gone blank and everything's gone to 0%. Is your one working for you?
Yeah, mine's still up here. So the next one was the primary types of hydraulic modelling that the attendees have been undertaking the past 2 years. So definitely predominantly that's 2D, closely followed by 1D. So we've only got a few people who have indicated 3D and CFD modelling. We've also mainly been looking at applications of flood hydraulics and floodplain management, but also with quite a few attendees involved in stormwater network design and urban drainage. Those were the main responses there. Now, you've also asked people how do they run models on the cloud, and if so, which platform? So most of the attendees, about 60%, say that they plan to run models on the cloud in the near future, with a handful of people already having tried some of these other platforms there. Jaap, can you still see those poll results? Did you have anything to add about that one?
I can still see them, and no, not really. I agree with you. I was wondering whether people were actually able to select a non-option or leave it blank, because otherwise they probably pick the plan one, and we might see a little bit of overrepresentation there. Gotcha. But you know, we're kind of assuming people might want to anyway. And I guess the final question, looks like most people are on NVIDIA. It's interesting to see that there are some people running on AMD. So particularly to those people, if you have specific questions, we'd be interested. We'll be talking more about NVIDIA during this talk, but I think the things we'll end up concluding are relevant to you as well. Other than that, nothing too surprising. relatively low percentage of people running models on GPU in the past, I guess. So that'll be interesting. But let's see where we end up. And please do ask your questions in the Q&A channel. We're very happy to take them at the end, and we'll have ample time for it.
Excellent, thank you. Well, without further ado, Greg, I believe you're presenting first.
Thank you, Tegan. Jaap, if you would kindly share your screen and we'll go to the first slide. Okay, yes, so welcome everyone to the talk here. Very often we give these webinars based around technical issues to do with hydraulic modeling, bridges and checking your model and cell size convergence and everything to do with actually being a flood modeler. But we have actually received quite a number of support queries over the past couple of years dealing with really more computer science and hardware type questions. So we thought it was, we did a webinar a couple of years ago talking about why GPUs were so amazing. But now what we're going to focus on in this webinar is actually how to make some of the hard choices about which ones you should be interested in buying or which ones you should be interested in renting. In order to get the most out of the TUFLOW software that you run. I will admit this webinar is a little bit unashamedly focused on TUFLOW and GPU because obviously that's what we do and it's what we do best. There will be some insights that you can glean out of this if you're primarily concerned about CPU compute. So feel free to also put those questions in the question and answer channel if you have particular CPU questions. But yeah, really we're going to be focusing a lot on GPU today, and we're also going to be trying to provide the sort of information that IT and systems staff need in order to help make decisions about what hardware to purchase or rent for the business overall as well. Sometimes there's a little bit of lack of communication between actually perhaps know exactly how the software works and what gets a good result. And sometimes the IT and systems department doesn't really quite understand that. So, we're trying to provide advice that actually can help those people as well to make good choices. I think that's enough of me waffling on. I think we'll get over to Jaap and we'll delve straight into the computer science of it. Thank you.
Yeah, thanks, Greg. Yeah, to get into it, a bit of an overview of what we'll be talking about today. Greg already said, we approach this from the TUFLOW side of things because that's what we work on. And of course, a lot of the engineers we work with use that primarily. I do think that the talk should be generally more broadly applicable and definitely not exclusive to the software. It's just that we gain our insights from that perspective. The questions we're looking to answer today are, what platform are we talking about? So I'll go into why we made those choices, what we're talking about today in a little bit more detail. But as was clear from the introduction on the webinar, what specs and metrics matter on the GPU, we'll be mostly talking about GPU. So it makes sense to talk a little bit more about what you should be looking at when you're selecting a GPU. Of course, there are still choices to be made in the rest of the hardware, so we'll go into that as well. And then as we're talking about it, you might get the sense that there's really only one answer and you just have to optimize for that. And the question is that actually true? Can one size fit all? Or are there other considerations? So we'll go into that a little bit. Something we won't talk about is how to optimize your model, even though that's arguably the most important thing, right? Like optimizing your model to run well and only run what needs to be run is going to save you much more time and cost than any piece of hardware ever can. But that's not something we're talking about today. I'm sure whatever you're using, the support for that software will be able to help you with that. Also, not talking about how to optimize your process and modeling pipeline. The model itself is one thing, but how you get your models to where they need to run, when you're running them, what you're running them on. We'll touch upon it a little bit, but it's not the focus of this talk. At the very end, we'll talk a little bit about trends we've noticed recently, current trends, and then we'll take your questions and answers. And if you have none, I've got a couple that are frequent for our support. Let's start with what platform we're talking about. So GPU accelerated model running over CPU accelerated model running, or basic CPU running. The simple reason we're talking about this is because GPU really is where the real performance gain is, and also where the hard choices to make are. So there's just hardly a comparison between what can be done on a GPU versus what can be done on a CPU. Most of the time spent in a model run is on the GPU. If your modeling software supports both, that's what you'll see. It spends its time on the GPU. It is important to note, maybe especially to the IT people, that this is particular to hydraulic modeling. So if you feel, or you feel you disagree, or you know of examples where it's really different, that's probably because it's not about hydraulic modeling. But when we're looking at hydraulic modeling, GPU seems to be king. It's where the models spend their time, and it's where there's way more room for growth. The second thing we want to make clear is we'll mostly be talking about NVIDIA. Again, I think it applies to the other architecture as well. It's not that we believe NVIDIA is better than AMD, but our experience is with it. And we found that it really pays to optimize to a specific architecture. And with our clients at the time and with our own consultants, we found that NVIDIA was the more obvious choice at the time, and we'd rather optimize for a specific architecture than do something like develop an OpenCL and then provide binaries for both architectures. The performance loss is substantial. We've considered it, with things like OpenCL to ROCm or porting our CUDA solutions with Hipify, but we've decided that optimizing first makes sense. And in the future, we might optimize for AMD separately as well and just come out with separate solutions. We're noticing that the same is true for other hydraulic modeling solutions. So, for example, Anuga and Riverflow 2D also appear to have made similar choices. A final point in terms of platform choice, we'll mostly be talking about our experiences with software on Windows. I don't think it's too relevant to the hardware conversation, but it is mostly what we're talking about. Keep in mind that we also developed TUFLOW AV, which primarily runs on Linux, so we do have quite a bit of experience over there. But Windows restricts us a little bit more, so it makes sense to talk about that. And we found that most of our audience sits in that space as well, and I think that's what the poll at the start also showed. Despite licensing performance and cloud benefits, most engines are now on Windows anyway, so it makes sense to focus on that in this conversation as well. So why do CPUs matter most? The simple answer is the number of cores, the number of operations they can perform in parallel. Where a CPU might have tens to hundreds of cores, a GPU will have thousands to tens of thousands of cores. And that means that it's ideal for parallelizable problems. It's optimized for exactly the kind of operations that matter and allowing us to scale up the computation way more than we could ever do on a CPU, even though individually the core of a CPU might be quite a bit faster than a GPU core. And obviously a CPU core is way more capable. It's capable of way more varied and general computation. GPUs are optimized for exactly the type of operations that matter. Plus, it has a parallel first architecture with fast global memory shared between cores instead of the multi-level hierarchy of a CPU, which is really useful if you're trying to do all kinds of things in parallel and doing all kinds of very varied tasks. But that's not what we're after within modeling. Making a choice for GPU, and this is another reason to focus on it most, making a choice for GPU has really decisive impact. On the one hand, your software may only support a specific technology, so you might only be able to look at certain types of GPU, and that really limits your choices anyway. But once you pick a GPU, it also dictates your power requirements, it dictates a specific system architecture. It might even decide whether you decide to go with desktop systems versus server systems, depending on the specific model of GPU you want to run, and all of the supporting hardware will be required. So it makes a lot of sense to look at the GPU first and then everything else. In terms of what the GPU is actually doing, a model engine spends a lot of its time on the GPU. And we found that for the type of modeling that we do in hydraulic modeling in general, most of that time is spent computing. There's not that much traffic back and forth. A lot of people will worry about the bandwidth to the GPU, looking at stuff like the PCI Express lane width, whether it's like a 16x lane or whatever. As it turns out, that's not as relevant for the type of modeling we do. There's the little graphic you see over there is a screenshot of a bit of a toy model doing something very similar to what most hydraulic models are doing. This is not TUFLOW specifically, this is just a simplified model. What it really clearly shows is that all those blue bars show when it's computing, and those tiny little red bars show you when it's actually transferring data to and from the GPU. It spends very little time in transfer. It spends an awful lot of time in compute. So you really want to optimize for the compute, and you don't need to worry as much about bandwidth to and from the GPU. What are the relevant GPU specs and metrics to think about then? Well, the number one thing that people will look at, this, you could say this is the megapixels of the GPU, is cores. And that's fair. If you look at otherwise comparable GPUs, more cores tends to be better, more parallelization, more jobs to run in parallel. But architecture really trumps cores or core count. And that's due to feature size. So newer architectures will have integrated circuits with smaller features, which means they can run more quickly. It's due to higher clock speeds. It's due to way better connectivity, both to the rest of the system, but also with the integrated components on the GPU internally. So getting hardware that has the latest architecture, even if you feel it's not getting you the most cores, is probably better. And it's better to spend a little bit on the improved architecture than on the very best and largest model you can get in the previous architecture. The other really relevant metric for a GPU is the amount of memory. As a really basic metric, the memory on the card needs to be enough to hold your larger models. That might mean that you get different models for different kinds of jobs. Not all of your runs will require the same amount of memory. So maybe not all of your modeling machines, if you have that many, might need the maximum amount of memory. But keep in mind that the size should be sufficient for your larger models. Also, keep in mind that, caching and bandwidth can trump size, but generally you want to aim for sufficient size on the card. Something that comes up quite a bit in support queries, and this is something we want to focus on as well, is the use of shared infrastructure. So having more than one user to a single GPU. I'll get into this in a little bit more detail in a moment, speaking about not using GPUs on VDI, or at least not in the way that many system administrators will advocate it. And the fact that you can split the larger server GPUs across multiple users. Something to also point out is that you can, of course, use a single GPU for multiple runs, and vice versa. You can use with most modeling software, definitely ours, definitely TUFLOW. You can use more than one GPU to serve a single user. So you can split your model and have it run across multiple GPUs, and the performance will hold up. So the performance is almost as if you'd had a single GPU with the combined number of cores and the combined amount of memory. So keep that in mind when selecting GPUs as well, right? Yes, you need enough memory to hold your entire model, but if you can split it across GPUs and you have that kind of space, that's a solution that might work as well. Greg, is there anything I'm missing here that you'd like to speak to?
Yeah, thanks, Sharp. No, I don't think there was anything really specific that I think you've missed. I think you've covered it all pretty well.
Excellent.
Yeah.
I'll keep going. Thank you.
Yeah, thanks.
Just a little bit more on sharing on VDI and MIG. So VDI stands for Virtual Desktop Infrastructure, will be a common three-letter acronym for system administrators. This is the kind of setup where many desktops running in a hosted environment on a server, something like a remote desktop server, for example, can share a single GPU or can share parts of several GPUs among them. This works really well when you're just running Windows applications, but not so much when you're trying to run a modeling engine that wants to take all the CUDA cores it needs for itself. This can't be overstated, the importance of this, because we very often get situations where people trial model runs on a specific piece of hardware and go, okay, this A100 is amazing for this kind of work. And then IT proceeds to implement 25 desktops, all sharing this one A100, which works fine if you're just running Windows. But as soon as you want to run a model, it wants to grab all those cores and a large chunk of that memory for itself. And obviously, you can't have 25 people doing that. I say obviously, but it's not that obvious because it seems to work just fine for all kinds of other applications that have way more up and down demands on the hardware. So keep that in mind. However, that doesn't mean you can't share GPUs in a server between multiple users. NVIDIA specifically has something called MIG, multi-instance GPU, and that allows a system administrator to take the GPU and logically break it up into multiple GPUs. So for example, a single NVIDIA A100, you could split it up into 7 GPUs, up to 7 GPUs, each with about 1/7 of the total. And each of those GPUs can then be used by a single model run on that server. Or you could even hand those GPUs over to a hypervisor, and then the VMs running on that hypervisor can make use of this one GPU. So a user using one desktop running on that hypervisor might be able to use that one slice of a GPU. And it feels like just having a regular GPU. In our experience, that performs as well as a 4070, 4080 GPU for the purposes of running a model. Do want to remark that we've found that there's substantial trouble getting this to work on if your base platform is Windows. So if you're running something like Hyper-V, you might run into some issues trying to get this to work. But if you have a hypervisor running that's essentially a Linux variant at its base or something like ESX, you should be able to do this. And then, of course, the VMs running on top of it, the client operating systems, should be able to make use of these GPUs, even if they are Windows machines. Getting to the rest of the hardware. So say you've selected the right kind of GPU, there's still some choices to make. What matters about the rest of the hardware? One thing that matters is the processor. You at least want enough cores to be able to run your model optimally on the GPU. And that roughly means that you should count about 1 CPU core alongside each GPU. So if you're running on 2 GPUs, you'd want 2 cores, and typically you want 1 or 2 cores extra to do some background processing. Do keep in mind that if you do model startup, it benefits a little bit more from having some cores on hand. Obviously, specific types of modeling might also benefit from more cores. An example being TUFLOW AV, which even in other types of runs still benefits from having a few more cores around. But purely from the GPU perspective, you basically want to pair it with about 1 CPU core. Post-processing, though, might benefit a lot from more CPU cores. So the choice of doing the post-processing on a modeling machine or moving the data somewhere else and doing the post-processing there might depend on how much CPU you have available there. Memory is another important aspect for the system itself. Previously, I was talking about the memory on the GPU. That should be enough for your model. But also keep in mind that you'll probably need 4 to 6 times the amount of memory that your GPU is using in your main system. So if you're running on an 8 gig graphics card, you're likely to need something like 32 gigs or well up from there, 48 gigs maybe even of system memory. And that goes pretty quickly, especially with the larger GPU cards nowadays, which might have as much as 24 gigs of RAM. If you keep that same ratio in mind, that means that you're needing 96 to 144 gigs of RAM for the system alone. And systems over 128 gigs are typically considered server grade. That limitation comes both from a motherboard, but also from the CPU architecture. So you'd want something like Xeon scalable processors with like Skylake, Cascade Lake, Ice Lake chipsets, or something like AMD's EPYC processors, like the Zen 2, Zen 3. Those will be able to address way more memory, but that really drives up the cost and the demands on the rest of the system you're selecting. In terms of storage, found that it's less important. A key piece of advice is to always write locally. So use storage that's on the machine itself and then ship off to other locations, not just for performance, but also for stability. The reliability of a network connection might not be such that you want to rely on it for the full duration of a run. We did find that using SSD over HDD is actually almost negligible. All of the other aspects make so much more of a difference that spending your money on SSD when you could have been spending it on a better GPU or more memory is probably not worth it. Obviously, for startup of the system and post-processing, your mileage may vary, but for model running, not so much. The main boards, it's mainly important that you keep the physical dimensions in mind. If you're planning to build a system that has 4 GPUs on it, it needs to be sufficiently durable, able to deliver all that power, able to transport data to all 4 of them, but also just physically fit them. This tends to be more of a problem than people realize when they first buy something. Even the case obviously matters, but especially the main board, you want to really look at this, whether there's sufficient space there. Of course, keep in mind that it needs to have a chip that allows for sufficient PCIe lanes and allows you to install sufficiently fast memory, because that will improve performance greatly as well. And then once you have all of that together, power is a real consideration. GPUs are very power-hungry devices. Running models on them will drive them up quite hard. So you can expect to hit the maximums of what's typically predicted for these kinds of cards. And with 4 GPUs and a bunch of storage and a serious mainboard running a lot of memory, you'll be using quite a bit of power. And since a computer is effectively just a really smart heater, keep in mind that this produces an awful lot of heat as well. You'll need a way to get rid of this heat, and water cooling for example, might be a solution. But it's not trivial, and it's not necessarily available for all the kinds of cards that you typically want to be using for your modeling. So keep in mind that you've got physical constraints to keep in mind as well. It's not just the number of cores or the amount of memory, etc. Something that is worth mentioning, even though it's not about hardware, think about your model configuration. What are you writing? How frequent do you need your outputs? And do you need everything for all your runs in the current phase of your project? If you're just calibrating, or if you're just designing, do you really need all the outputs that you'll need during production, or vice versa? Maybe you just need specific outputs during calibration because you're looking at finer detail, but you don't need specific outputs when you're running production runs. Keep that in mind. Consider your model configuration first, and don't worry about the hardware too much before you get there. And another important point to make is automate. If you're clever at automation, you'll save a lot more money and a lot more time than when you just get really expensive hardware. We find that just a lot of time and money is wasted in inefficiency. Moving data around is a lot more efficient than getting way more storage and creating copies everywhere. Teaching your engineers how to write automation scripting and then spending time on it is really a good use of their time, especially because engineers' time is the most pricey thing you have to consider in general. So if you can automate part of the job they're doing, that's almost always worth it. And nowadays, script coding is in everyone's reach with AIs like ChatGPT and Claude, etc., able to not just teach you how to code, but also do part of the coding for you. There really is no excuse to at least look at automation. And consider stuff like PowerShell and Bash and Batch as well as Python, JavaScript, Go, etc. It's not just the serious languages that you need. Even just basic automation with something like PowerShell can save you an awful lot of trouble or mistakes. Once you've written and tested your scripts, that saves a lot of mistakes as well, and that could be way more costly than the hardware you're looking at. Having said all of that, you can look at numbers and metrics all day and automate and optimize your model. But in the end, whether your model will run optimally is best decided using benchmarks. How fast your model runs on the hardware is ultimately what matters. And then, your specific model, maybe not so much, but the kind of model you typically run. Now, if you're lucky, there's already benchmarks out there for the kinds of models you run, and you can just look at those. It's also possible that you don't really have access to the hardware you'd like to run your model on, but you'd still like to make a decision on whether it would perform better. What we found is there's actually decent proxies to be found. If you look, for example, at pass mark benchmarks, they correlate quite well with the runtime of our HPC modeling. One thing you would note from this particular chart is the gaming GPUs all sit nicely grouped around a certain line, but you'll notice that the tested server GPUs are actually more or less in their own space. They still correlate very well, so a higher pass mark score correlates with better HPC speed, but you shouldn't compare server hardware with desktop hardware in this context. So keep that in mind. We also provide benchmark models, and I think more modeling software does. It makes sense to actually grab one of the benchmark models and run a standard benchmark on your hardware to see how it compares to what's typical. It might tell you something about whether your hardware is not optimally configured for the card you're using. It might also just provide a specific data point for specific hardware that the vendor of your software didn't get around to testing yet. I guess, Greg, could you talk a little bit more to this data?
Yes, thank you. Yeah, sorry, I was deep in the question and answers, rapidly typing and firing them all off.
Important.
Yeah, look, the really interesting thing that shows up on this chart here is that, you know, the series from the 10XX series to the 20XX to the 30XX to the 40XX. Now, these are all the gaming GPUs. That series there, you can see that there's a fairly, you know, consistent trend and improvement, and that's to be expected. However, right at the very top end there, you can kind of see that the 4080 and 4090, they're perhaps not quite keeping up with the dotted line, with the rapid gains that we saw in the previous, you know, 10 years or so since the inception of CUDA. But still, it's a pretty strong correlation. And it's a fairly useful one, showing how that, you know, just when you throw more and more cores at the problem, you generally will get a faster result. Where you find you'll get outliers on this graph is when you change the significant GPU architecture. So if you change from the gaming series to one of the, you know, Quadro series, or going to the scientific series, what used to be the Tesla, which then become the V100 and then the A100, and now we've got the H100 as well, which we haven't even tested TUFLOW on yet. When you change to those other GPUs, you'll find that you'll get a significantly greater performance out of them for the same core count as on this plot. So it kind of is a little bit architecture dependent. Where this is going to go in the future, I don't know. We're going to see, you know, processors get down to the 2 nanometer scales, and possibly even smaller. I'm not even sure what the limit will be before you start running into quantum effects on these devices. So, you know, the future is still very promising. I think there is a lot of room to go yet. And if Jaap hasn't already made the point, you know, for the previous decade, a lot of the driving impetus behind this was people, you know, wanting to have the best graphics for their games. Whereas now what we're seeing with the AI revolution is that people are realizing that, you know, when computers can almost think like a human, that's an incredibly powerful commodity. And the GPU technology is what is enabling that. So I think we're going to see substantial investment in compute technology, especially still on the current GPU platform. We're going to see substantial investment in that over the next decade as well. And it's just they'll find a way to keep improving the performance of these devices into the future. I think I've said about all I can there, yeah.
No, thanks, Greg. I appreciate it. Yeah, just a small remark on the side there. You mentioned the Quadro cards as compared perhaps to the other GeForce cards. We found that although they do perform better, so if you need the very best thing, that might still be an option. In terms of price on the compute, the GeForce cards are still superior. but fairly much in line with server cards. So the Quadros really are slightly better for on the core count. And if you really need something in a desktop that outperforms the GeForces in the same class, you might go that direction. But in terms of cost, you might be able to build two systems with GeForce cards for lower cost than actually getting all Quadros. So that's something to consider as well. And that's why you'll see most of our cards and our tests in the benchmark data actually being GeForce cards. People noticing or looking at this chart really closely might go, well, actually, there's a mistake there. There's one card that's marked as being from the Turing series when it's actually from the Volta series. Just as a small aside, if you see all those numbers and letters like A100, etc., the K80, those letters are just the different architectures, and the numbers are just model numbers. So the numbers are essentially meaningless. The letters in order, as shown over here, just represent the various architectures that NVIDIA has brought out. And like Greg already mentioned, we're currently at the H100s and I think the L40s in the data center. So we're at the H and L level right now. But the A100s are still more or less king. I think Tesla just built a data center with 10,000 H100s. So I guess that's going to be the new normal. From what I've been saying so far, you might conclude, okay, so all I need is to get the very fastest GPU, and that's it. That's not necessarily true. You have to consider a few things. Consider that model design and calibration have different requirements than production runs. Design and calibration benefit most from minimizing your runtime, because otherwise you're just taking up more of the engineer's time, and ultimately that's still the highest cost. Keep in mind that time on license versus time on hardware can matter, right? We're mostly talking about hardware, and faster hardware allows you to get more models through, which means they spend less time on the hardware, so it's worth spending more money on it. But of course, if you run them faster, you might also make better use of the licenses you have. Slower will be better for hardware and power cost, but there's a balance there. And in owning versus renting, I think a lot of these conversations go in the direction of, should we be talking about cloud versus desktop? I think that's a bit of a skewed perspective. I think it's more about whether you own the compute or you rent it. Owning could be desktop servers, but also semi-permanent cloud servers. Renting tends to be stuff like pay-as-you-go on the cloud, software as a service, platform as a service, or even if you can find an organization willing to do so, having someone else run the models for you. When you rent, you run into all kinds of additional complexities. You need to provision the compute, you need to deal with licensing in an environment that's not yours. You need to get your data in and you need to get your data out. So there's complexities there. So that drives up the cost. So although renting can look interesting when you only need to do stuff in bursts, there's still a lot of other aspects to consider there as well. Ultimately, it's more about finding the right mix. So make sure you do have sufficient fast compute for your design and calibration phase, but look more at balancing it for your production. If you have fast hardware, it does allow you to save some time in design, right? Because you can get the result more quickly and try something instead of having to come up with doing wide parameter scans and running lots of models in parallel, because you won't know the answer for several days. Another tip to give here is consider the fact that your engineers could be developing models on CPU workstations and then run them for production or fully run the model later on a GPU machine. It's often as simple as a command line option, which models like TUFLOW will allow. It's the same model. It'll start up on CPU. And once it starts up, you might consider then actually running it on a GPU machine. If your business is so small that you don't really have the luxury of thinking about, I need X of this and Y of that, I just have a few machines, the basic answer will still be, you probably should get the fastest. It's almost always worth it. You want to balance the purchase of more hardware with the cost of licenses. But ultimately, if your licenses are pricey, getting fast hardware is often a good trade-off. Do keep in mind that you need to keep the long view. If you're looking at it today, whatever hardware you buy will age, and it will become the lower end later on. So if you have a workflow that keeps in mind that there's low-end systems and high-end systems, that will benefit you even if you're starting from scratch right now and getting new hardware. The cloud can be better in certain cases, but really an important thing to note over there is you need to be prepared. Like when you prepare for on-demand computing, that does allow you to scale for a large project or an emergency. You need to get it done before the next weekend. But if you plan to use the cloud only in emergencies, but you don't actually plan and prepare to use it, you're just causing another emergency. So keep that in mind. If the cloud is part of your solution, you need to do it and test it and make sure you can do it tomorrow. Otherwise, you'll just run into more trouble. And another thing to consider there is whether perhaps you can bring your entire process into the data center or cloud, because that eliminates a lot of the problems. If your licenses live in the cloud, if your data lives in the cloud, if your data processing lives in the cloud, and you don't find yourself constantly moving stuff in and out, that might actually tip the scales in favor of the cloud in general. If you're not ready to do that, or if it's just cost prohibitive due to scale, you might just be looking at getting better local hardware. Before we get to questions and answers, just want to point out a few trends that we've noticed. The most important one to underline here is we're convinced CPU will not catch up. Most, if not all, engines for hydraulic modeling will move over to GPU over time. Many of them already have. Some of them are in the process, and I don't think the engineers generally disagree. It's hard, but it's worth doing, and as a result, we expect all of them to do it at some point. Another trend, of course, can't have this conversation without bringing up AI, and I think Greg already did as well. AI has driven a lot of innovation in high-performance GPUs, and it's well beyond what games require. So far, we've mostly had users that use gaming hardware. But these AI developments drive innovation in a direction that benefits hydraulic modeling as well. And we'll see more and more that server compute will far exceed what desktop compute for gaming allows, making different solutions really come into focus where previously they were just not competing because either too small or too specialized. Sort of alongside that, hop and allow desktops are now being replaced with more shared and central compute. This is in part thanks to the pandemic, I guess you could say. People want to work from home more, so putting the machine somewhere where they can remotely reach it makes more sense. But obviously, this also allows putting more compute into a single box and allowing multiple users to log into it and share it. So that's a common trend we see as well. As Greg previously pointed out, we're not really seeing any signs of slowing in GPU technology. It's still steadily rising. Newer GPUs are still faster than the previous ones. And this is not a Moore's Law thing, because Moore's Law talks about the individual integrated circuit becoming faster, whereas GPUs still benefit from putting more and more of them on a single device. And that doesn't seem to be slowing down anytime soon. Yes, this to wrap up, I guess individual cards have gone well beyond what a single model needs. But if your model allows you to have multiple models running on a single GPU, it's still worth getting the later architecture. The later architecture still makes each individual model run faster. And if you can share a single GPU, that's clearly worth it. And it also speaks towards multiple users sharing a single system. And something to keep in mind when you're building these systems, it used to be possible to take 4 decent GPUs and stick them in a single machine. But given power requirements and space requirements and heat production, that's getting harder and harder unless you really look at specialized hardware, suitable for rack mounting. So keep that in mind as well. It used to be a reasonable proposition. We're finding that it's getting harder and harder unless you're really investing into sizable hardware. So with that, I would like to get to some questions and answers. I guess I'll hand over to you, Mitch, to see what the top questions are here.
Yeah, thank you for that, Jaap. Yeah, Mitch, go ahead. I know you've been answering feverishly in the background there. Greg's been on it as well, helping out. So if you've got some of the topics that have been upvoted a bit more.
Yeah, thanks, Tegan. Yeah, our fingers have been firing away rapidly. Please continue to send your questions through, and we'll do our best to answer all of them. I went from Stephen. As a new hydraulic flood modeler, less than 2 years, I've been using HEC-RAS, which uses primarily CPU cores, but I'm quite curious about other options. His company's been looking into moving more into cloud modeling, especially since many of the modelers are working remotely. Would you recommend going down this pathway for cloud? And is the transition from local computing to cloud relatively smooth, or is there some tricks in that? Sorry about the double barrel question there.
Right, yeah, this seems to be a bit of a double question. I guess the answer to the last bit first, is the transition from local computing to cloud relatively smooth? It really depends on whether you want to scale up when going to cloud, as well as just moving from one place to another. Cloud computing really isn't that different from local computing. So from that point of view, it could be very smooth. Just getting a VM up and running in the cloud is almost trivial. But if you're looking to automate running jobs in the cloud and do many model runs in parallel on many machines, there's quite a bit of some upskilling required to get that done. It's not rocket science, but don't underestimate it. And like I pointed out previously, moving your data up there might be more trouble than you realize and take more time. We've had situations where we were able to run many models in parallel, get through hundreds, close to 1,000 model runs in a very short period of time, only to find that it would take the client several days to download the data. And obviously that kind of throws away the entire advantage. So keep that in mind as well. I'm sorry to say I forgot the first half of your question. Could you repeat for me, Mitch?
Yeah, it was more just, would you recommend moving up to the cloud, which I think you probably have answered there. Cool. All right. We did. So Luke had a question about the RAM usage. Is there a good way to estimate how much RAM will be required? We mentioned sort of 5 million cells per gigabyte of GPU RAM. Greg, with the subgrid scale sampling side of it in TUFLOW, is that still relevant? Or is it sort of needing more resolution?
Yeah, the subgrid scale does use a little bit more memory. I think it's somewhere between 10% and 20% more memory in order to run a model with subgrid scale versus without subgrid scale. However, the benefits that you get from the subgrid scale are fairly significant. In many situations, you will find that you can run a model at a reasonably coarser resolution with subgrid sampling on, and you'll get an equal quality hydraulic result compared to running it as a fine resolution without subgrid scale. So yeah, subgrid scale definitely uses a little bit more memory. As a general rule, we recommend typically about 4 times. If you think you're going to max out the GPU memory with a TUFLOW HPC model and your GPU has got 11 gigabytes, then the actual amount of CPU RAM that you need to pre-process and get the model set up ready to go can be as more like 40 something, 50 or 50 gigabytes. So you've got to multiply it up by about 4 to get the model spun up and running. If you're running TUFLOW with the quad tree mesh capability as well, then that number of 4 can actually become a little bit even higher. It can be 5 or 6 at a maximum, I would say 6. Does that answer the question?
Yeah, it's great. Thank you, Greg. This one's coming at you as well, Greg. There's a couple of good questions from Aaron, which you've answered, but I'll just throw them to the floor. What are the challenges in implementing AMD's GPU and ROCm for HPC? I don't even know what ROCm is, so you have to inform me on that one.
Yeah, look, we've used the NVIDIA toolkit for many years because they made it very easy to get started with GPU programming, and that's how I got started. I needed it easy. And as a result, we're kind of locked into NVIDIA, but we've been happy about that because consistently what I've seen over the past number of years is that the NVIDIA compiler seems to give really, really good optimizations, and the compute performance out of the NVIDIA cards is usually better than you can achieve with the OpenCL API and the AMD cards. In terms of graphics capability, the AMD cards, I don't think they're necessarily any behind where NVIDIA is at. But in terms of compute, it seems that the NVIDIA compiler just seems to be able to get really good optimizations in there, and it's been the sweet spot for scientific computing for quite some time. In order to support AMD cards, we would need to move across to supporting the OpenCL driver API. I have done a little bit of that in the past, but it would be a fair bit of effort to convert all of the TUFLOW HPC code base to be able to use either OpenCL or NVIDIA. And we haven't had enough of our users really saying that, we're giving up on TUFLOW because you don't support AMD, or we're not going to use TUFLOW because we don't support AMD. We kind of think that, if you're going to learn how to use TUFLOW and you're going to pay to buy licenses to run on GPUs, then, the decision then as to which hardware to buy is somewhat subservient to those prior choices that you've made. And, I don't think it's too big a deal to say, look, just buy an NVIDIA GPU if you want to run HPC.
Thank you, Greg. I'll open this one up to both of you. When you were talking about CPU cores, were you meaning physical cores or hyper-threading? And does that affect the hyper-threading affect any of the computing that you're doing with TUFLOW?
Yeah, I might be able to comment a little bit more on that. And in my experience, I haven't really seen a significant improvement in compute by turning hyper-threading on and running, if you've got a machine that's got 4 CPU cores, but you turn hyper-threading on, so you run 8 threads on the 4 cores, I haven't really seen a substantial improvement in performance by doing that compared to just running on 4 cores. And in fact, a few years ago, when I was at the Bureau of Meteorology, all of their compute nodes in their very, very large, expensive weather computing machine, all of the compute nodes in that had the hyper-threading turned off because they had found the optimum settings was not to run hyper-threading. It probably depends a little bit on software.
Yeah, I think it very much depends on software. A CPU is a general purpose machine, and it does way more than just dry compute, right? Like when you're computing a certain model, you know exactly what you need to compute, you know what the next step is going to be, and you just need to get through the operations as quickly as possible. What a modern CPU is doing is way more. There's all kinds of parallelization. There's lots of downloading going on in the background. It's a way more complex beast, and that's where hyper-threading really shines, because it allows switching between different tasks that both need a little bit of compute done, while also a lot of other stuff is happening in the background. That's not really true for compute. So we find that for CPU-based compute, it simply just makes more sense to have 1 thread per core, and so the number of threads you're running your simulation on tends to be equal to the number of cores you have available. Hyper-threading doesn't figure into it.
We may have covered this one a little bit before, but it's still an interesting point, is that in their experience, that the cloud computing side of things for hydraulic modeling is probably still not where it needs to be. Do you have any, in terms of getting runs done and getting them up there, do you have any good advice or any intel on future developments in this space to help people doing this kind of work on the cloud?
Yeah, I feel like it's a very broad question. What's your interpretation of the question, Mitch? I'm not sure if I understand the question fully.
I think it is, are there things being done to help hydraulic modelers run models on the cloud, or that you've seen? Or
well, there are. So, right, yeah, thanks. That does help. So yes, we're working with both AWS and Microsoft directly, having engineers from their platforms actually work with our software to see how it performs on the various hardware options they have to offer, and also to see whether what they're currently offering actually suits the needs of our kinds of workload. We found, for example, that if you get really high-end compute nodes in the cloud with the GPU you like you might want to use an A100, you tend to get way much of all of the other compute as well. Way too many virtual cores, way too much memory, and far too much storage than you really need. You're still paying for it though. So from that point of view, cloud is very inefficient to be using for hydraulic modeling, even though the hardware that's available in the cloud is amazing. And this is news to these parties. They don't realize that the kind of modeling or the kind of compute required for hydraulic modeling is just substantially different from what they're used to. So that's something that's happening. These companies, AWS and Microsoft or Amazon, and especially in this context, probably wise to specifically point out that they're Amazon. Amazon and Microsoft are working with us, and I'm assuming other vendors as well, to really wrap their head around it. So that's one of the things we're doing. Other than that, I know a lot of consultancies are working on developing their own tooling to, streamline the workflow. And that's kind of getting back to the point I was talking about previously. Like, that's really what you want to be looking at, optimizing scheduling, because cloud hardware is fast, but it's also expensive. So you really want to make optimum use of it if you are using it. So there's developments in that area going on as well. Hope that answers it.
Thanks, yeah, that's good. I reckon we've got time for 2 more questions. This one's for you as well, Jaap. You say storage and writing locally. If you had an 8 GB fiber channel connected SAN storage, directly connected, not mapped, would that be a sufficient way of saving results from the network?
If you're willing to rely on it, probably. If you're looking at that kind of storage, the bandwidth is probably going to be very similar to writing to a local hard drive. So sure, yeah. If you're in control over how it's connected and it's hardware you're managing yourself, I wouldn't recommend against it. In fact, I would almost say that storage effectively is local, right? Because if you're running that kind of kit, you're probably also running VMs instead of just running directly on the hardware. And that'll be as local as the storage gets to those machines. What we're really saying when we're saying write locally is don't write to network shares, don't write over network connections, keep that complexity out of the connection. Write locally to the storage that's directly attached to your VM, whether that's in the physical hardware locally or really near on the network through simple connections.
Thanks, yeah. Greg, I can see you're punching away on a question there, but I've got another one for you here. Does TUFLOW scale across more than 2 GPUs effectively? We seem to notice a bit of a drop-off when we start to include the third card.
Yes, it does scale across 2 GPUs quite well, but I mean, up to 3 or 4, we've tested it to 4. It really does require the decent size model though. Generally, if you've got a model that's between 1 and 10 million cells, it will scale quite well to 2 GPUs, but going to 3, you might find that there's minimal extra improvement there, basically because you've now got, effectively, you've got, twice as many copies that you're having to do for moving edge data around between the model domains back and forth between the GPUs. Once you're running models that are 20, 50, 100 million cells, you'll find that you get, that if you run it on 4 GPUs, it will generally run over 3 times faster than running on 1 GPU, which is getting to be fairly good scaling once you get to the really big models. But for the 1 to 10 million cell region, it should run on 3 faster than 2. But if you're doing the calibration stage of your project and you just need to get runs done really fast and make a decision about the results in order to change the model for the next run, then throw all your resources at it and spread it across multiple GPUs. But if you're at a stage in the project where you're trying to do what you might call production runs, where you've got lots of models to run, but they don't depend on each other, they can all run together, then then spread them around. I mean, that's provided that you've got the licenses for it, of course.
Okay, thank you very much, Greg. We've got a few questions. Unfortunately, we haven't had time to answer. We'll get those together and we'll send them out to the people that have attended. So we'll have to wrap it up there. I'll throw back over to Tegan, and thanks very much. If you do have any other final questions, please send them through.
Thank you very much, Mitch. And yes, big thank you to our presenters, Greg Collicutt and Jaap van der Velde, for your effort preparing the presentation today for the AWS and for sharing your wealth of knowledge, and also for Mitch for fielding all the questions. There's been a lot, obviously we didn't quite get through them, but as you said, we'll send through some more answers. It's been really useful, practical information for our attendees, and I'm sure that our audience have found this advice highly interesting and valuable, so thank you again. So before we close off, just a few housekeeping reminders. So the recording of the session will be made available, and live attendees will be emailed a certificate of attendance, which is great for collecting your CPD hours. So definitely make sure you grab that. Please also take a minute to fill out the feedback survey for the AWS that will pop up. That is really important for guiding their future content. So there are a number of AWS webinars and live courses coming up. Please just go to the AWS website, which is www.awschool.com.au, and you can register there for those that you're interested in. And also don't forget that there are numerous resources for training on TUFLOW's website, www.tuflow.com. So thank you again for your attendance today, everyone, and to our presenters, and we'll see you all again next time. Thank you.